So let's discuss Pauli Spin Matrices and their properties. So first of all, let's see Pauli Spin Matrices. So like orbital angular momentum operators Lx, Ly, Lz, the spin operators Sx, Sy and Sz are to be associated with the components of spin angular momentum. So just we have Lx, Ly, Lz has the components of angular momentum, that is orbital angular momentum. In the same way, Sx, Sy and Sz are the components of spin angular momentum. Satisfy the commutation relations. So just like we have commutation of Lx, Ly is equals to I h cut Lz, and commutation of Ly, Lz is equals to I h cut Lx, and commutation of Lz, Lx is equals to I h cut Ly. In the same manner, here also we are having the similar kind of relationship for commutator relations for this spin operators also, spin components also, that is commutation of Sx, Sy, that is nothing but Sx, Sy minus Sy, Sx, that is nothing but commutation of AB formula is nothing but AB minus BA. We have commutation formula. So here in the place of A, Sx, in the place of B, Sy, so AB minus BA. So finally we get IH cut Sz. So here if we see, Sx has the component of angular momentum because it is angular momentum, and Sy also has the component of angular momentum. So product of them both, so it must be having dimensions of angular momentum square. So in the result, if we see, we are having IH cut Sz. Here Sz is already having angular momentum dimensions. So we have got one of the angular momentum dimensions, and h cut also has the dimensions of angular momentum because delta x into delta p based on uncertainty principle must be greater than or equal to h cut by 2. So from there we can say that momentum into position, so that is nothing but angular momentum, so MVR. So hence h cut has angular momentum dimensions and Sz also has angular momentum dimensions. So we can just tally the commutator relations. So this is in this way can tally this relationship. So in the same way for commutation of Sy, Sz, we are having IH cut Sx, and commutation of Sz, Sx, we are having IH cut Sy. And next thing is, if we consider the case with spin is equal to half, that is electron, then according to Uhlenbeck and Goudspeed hypothesis, each of the operators Sx, Sy and Sz must have two eigenvalues, h cut by 2 and minus h cut by 2. So for spin half, electrons would be having spin half. So on that basis, we should have eigenvalues equal to h cut by 2 and minus h cut by 2. Now introduce new auxiliary operators sigma x, sigma y and sigma z such that, so here they have given the relationship between Sx and some these operators sigma x, sigma y and sigma z. So Sx is nothing but half h cut sigma x, and Sy is nothing but half h cut sigma y, and Sz is nothing but half h cut sigma z. So the following properties of sigmas may be noted. So from this we can note the following properties. So what are all those properties means, since the eigenvalues of each S are to be just half h cut and minus half h cut, so here we should get h cut or half h cut each of S. The eigenvalues of each sigma must be plus 1 and minus 1. So half h cut into 1 plus half h cut. So half h cut into minus 1, half h cut into minus 1 minus half h cut. So on this basis, so they are saying from this we can say the eigenvalues of sigma must be plus 1 or minus 1, because we might be having h cut by 2 or minus h cut by 2. So here if we want h cut by 2, in the place of sigma y we can have 1, and a h minus h cut by 2 means in the place of sigma z we can have minus 1. So each of the operators sigma x square, sigma y square and sigma z square must therefore have only the eigenvalue 1, and such operator is only the unit operator. So here if we see, so this is based on eigenvalue relations. So if A is a matrix and lambda is its one of its eigenvalue, and then lambda square would be the eigenvalue of A square matrix. So here they are saying sigmas must be having eigenvalues plus 1 or minus 1. Then sigma square has plus 1 whole square, that is equals to 1, and minus 1 whole square, that is equals to 1. So sigma square must have only 1 as its eigenvalues. So this one eigenvalue is only possible with identity matrix. So this is identity matrix 1 0 0 1. So A minus lambda I, this is the equals to 0 characteristic equation. So if we substitute in this in the place of A I, so what we would get? 1 minus lambda lambda I minus lambda 0 0 1 minus lambda. So this determinant must be equal to 0. So 1 minus lambda into 1 minus lambda minus 0 equals to 0. So 1 minus lambda whole square, that means lambda equals to 1. So identity matrix is the only matrix which has the eigenvalue 1. So as we are getting, sigma squares must be having only 1 has their eigenvalue. So only possibility is sigma squares must be equal to identity matrix. So therefore we are having sigma x square is equals to sigma y square is equals to sigma z square equals to 1 here. So on the next thing is, according to 2 and 3, the commutation rules satisfied by sigmas must be. So on the basis of this 2 and 3, it's on the basis of 2 and 1. So on the basis of 2 and 1, the commutation rule satisfied by sigmas must be. So what we have to do is, in the place of Sx, we have to substitute half h cut sigma x, Sy half h cut sigma y, Sz half h cut sigma z in these equations. So if we do so, here also, if we do so, we would get this equation. Finally, if we do simplification, finally we will get this equation. So based on this equation 2 and this commutator relation 1. So if we just substitute in the place of Sx sigma half h cut sigma x. So after multiplication here and here, half h cut sigma z. So here also we will get h cut square, here also we will get h cut square. So both of them would be cancelled, and h cut here 2 times h cut by 2, here only 1 time h cut by 2. So 2 cancel, 1 2 would be remaining there. So that will go to that side. So finally we would be having 2i sigma z. So in this manner. So finally from this 2 and equation 1, we would have the following commutator relations for these sigmas. That is, commutation of sigma x sigma y is equals to 2i sigma z, and commutation of sigma y sigma z equals to 2i sigma x, and commutation of sigma z sigma x is equals to 2i sigma y based on this second and equation 1. So on the next thing is so 2i sigma x, 2i into sigma x sigma y plus sigma y sigma z. So they are finding out this thing. Now 2i. Now if we multiply inside, so this is a constant. So if we multiply inside, so it is of the form a into b plus c, that is nothing but ab plus bc. So if we after multiplication, so here we are having sigma x, so 2i into sigma x, here also sigma x. So this constant is included with this 2i sigma x, and And as we already know, 2i sigma x is nothing but sigma x sigma y. 2i sigma x is nothing but commutation of sigma y sigma z. That is here, from here, 2i sigma x is nothing but commutation of sigma y sigma z. So that one we have to substitute here. So commutation of sigma y sigma z is nothing but sigma y sigma z minus sigma z sigma y. So we are having this thing. So here also the same thing we have to replace. And now finally we have to do product. So here this sigma y is being multiplied from the right hand side. So here if it is being multiplied from right hand side, we have to keep it at right hand side only. If it is getting multiplied from left hand side, we have to keep at left hand side only, because this is here, these are nothing but commutators. They are of the matrices form. So AB is not equals to BA. Hence if it is getting multiplied from right hand side, we have to multiply in that manner only. So after multiplying right from the right hand side, so already we are having sigma y sigma z, so sigma y, and here sigma z, already sigma y, so sigma y square, and here also sigma y square, and here sigma y sigma z sigma y. Here these both terms are same. It's like ABA, here also ABA. So both of them will get cancelled. And here if we see, finally this terms will be remaining, but we know that sigma y square is nothing but 1 from the on the basis of eigenvalue. So sigma x square, sigma y square, sigma z square is equals to 1. All of them are equal to 1. So this will be 1, this also would be 1. So minus sigma z plus sigma z. So both of them would get cancelled, and finally we would be having 0. So this is nothing but 0. So 2i sigma x into sigma x sigma y plus sigma y sigma x is nothing but 0. That is nothing but, if we send this 2i that side, 0 by 2i, that is also, this is nothing but 0. Hence we would be having sigma x sigma y is also minus sigma y sigma x. So that sigma x and sigma y anti-commute. So this is also an important property of Pauli spin matrices. So here we are actually deriving Pauli spin matrices here. So we found this property in this derivation. So similarly, any two of the sigmas anti-commute in pairs, that is sigma x sigma y plus sigma y sigma x equals 0. In the same way, sigma y sigma z plus sigma z sigma y equals to 0. Here we are not having minus in the middle. So what is commutation of a comma b? That is nothing but ab minus ba. And anti-commutation of a comma b is nothing but ab plus ba. So that is nothing but equals to 0. And from equations 4 and 5 we have, that is from this and this equations. So here what we have to do is, this is first equation. This equation must be added to this equation. So if we add, these terms would get cancelled, this term. So on 0 plus 2i sigma z is nothing but 2i sigma z. And finally here also sigma x sigma y, sigma x sigma y, both of them would add up to 2 sigma x sigma y. So finally we would be having 2 sigma x sigma y equals to 2i sigma z. So both side 2 gets cancelled. So finally sigma x sigma y is equals to I sigma z. So finally we will be having, so if we solve these 3 equations with this corresponding 3 equations, we would get these following relations, that is sigma x sigma y equals to I sigma z. In the same manner remaining also, since each sigma has 2 eigenvalues, so 2 by 2 matrix may be expected to fulfill the purpose, and we begin by associating with sigma z the simplest 2 by 2 matrix having eigenvalues +1 and -1. So here we have already seen that sigmas must be having eigenvalues +1 or -1. So they are having 2 eigenvalues. So for 2 eigenvalues, it is sufficient if we have a 2 by 2 matrix. If there are 3, then we have to take 3 by 3 matrix. 4 means 4 by 4 matrix. So only 2 eigenvalues. So we can start with 2 by 2 matrix. So sigma z is equals to 1 0 0 -1. So here if we do a minus lambda I equals to determinant of a minus lambda I equals to 0, 1 minus lambda minus 1 minus lambda, so lambda equals to minus 1, lambda equals to plus 1, we would be having the eigenvalues 1 and minus 1. Here also if we see determinant ab minus ba, determinant for this determinant ad minus ba, so 1 into minus 1 minus 1 minus 0 minus 1. So actually for any matrix, product of its eigenvalues is equals to its determinant. So we can design sigma z matrix in this manner because 1 and minus 1 are the eigenvalues of sigmas. So here we are having 1 minus 1. If we do a minus lambda I, determinant of a minus lambda I equals to 0, finally in the place of lambda we would get same 1 and minus 1. Also if we cross check determinant of this matrix AD minus BA, so minus 1 minus 0 minus 1. So product determinant is always equals to of a matrix is equal to product of its eigenvalues. So here eigenvalues are 1 and minus 1. So 1 into minus 1 is nothing but minus 1. And next thing is, now we have, so we don't know sigma, we are just taking sigma z in this manner and we don't know sigma y and sigma x. So we need to find out that one. So for that we are placing here in this manner. So we don't know what could be sigma x matrix. So we are taking this form A, B, C, D. These are all unknowns. Now if we multiply, so A into 1 A plus B into 0 0, A into 0 0, B into minus 1 minus B, C into 1 C plus D into 0 0, so C plus 0, C into 0 0, D into minus 1 minus D. So matrix multiplication. In the same way, sigma z into sigma x. So sigma z is this and sigma x we don't know. So 1 into A, 0 into C, 0, so A. 1 into B, 0 into D, 0, so only B. 0 into A, 0, minus 1 into C, minus C. 0 into B, 0, minus 1 into D, minus D. So finally we are having these terms. But sigma x and sigma z anti-commute. So we already know that sigma z, sigma x plus sigma x, sigma z equals to 0. So now on adding this both, we must get 0. So on adding here, we must have 0. So on adding corresponding elements, a plus a, 2a, minus b plus b, 0, c minus c, 0, and minus d, minus 2d equals to 0. This yields, so we must get finally a null matrix. That means in null matrix, each of the elements must be equal to 0. So here already these both are 0. So 2a must also be 0. So 2a equals to 0 means a equals to 0 and minus 2d equals to 0 means d is 0. So every matrix that anti-commutes with sigma z such as sigma x, sigma y must have the form. So we already know that sigma x, sigma y, sigma z anti-commute with each others. So it must have this form, that is a and d must be 0. So in this form a and d must be 0. So 0, b, c, 0. That would be remaining. As the eigenvalues of sigma x, sigma y are plus 1 and minus 1, simply we can take b equals to c equals to 1. So eigenvalues must be plus 1 or minus 1. So bc equals to 1. So if we take bc equals to 1, what will happen? So here bc must be equal to 1 they are saying, that is 0, 1, 1, 0. So if you find determinant of this matrix, so determinant if you find is it would be equal to AD minus BC. So 0 minus 1, 0, 0 into 0 minus 1 into 1, 0 minus 1 minus 1. So determinant is minus 1. Already we know that eigenvalues of sigmas are plus 1 and minus 1. So product of this eigenvalues 1 into minus 1 minus 1 must be equal to determinant of the matrix. So in this simplest form, we are having determinant of the matrix minus 1 and product of eigenvalues also minus 1. Hence this is another simplest form. And then follows sigma y equals to 0 minus I 0. here also if we do determinant of this AD minus BA, so 0 into 0, 0 minus I into I. Already we are having minus, so AD minus BC. So there one minus and here one minus, minus into minus plus, and I into I is nothing but I square minus 1. So finally we would have minus 1 as the determinant of this matrix. Hence this is another possible case. So therefore sigma x is 0 1 1 0 and sigma y is 0 minus I 0 and sigma z is 1 0 0 minus 1. So these matrices are called Pauli spin matrices associated with the components of spin angular momentum. So these are the Pauli spin matrices and they are associated with spin angular momentum, that is Sx is also half h cut sigma x. In the place of sigma x we are having 0 1 1 0 and Sy half h cut sigma y. So in the place of sigma y 0 minus I 0 and in the place of Sz is equal to half h cut sigma z 1 0 0 minus 1. So these are nothing but Pauli spin matrices. So in this manner we have derived Pauli spin matrices by step procedure. These are same as Jx, Jy and Jz in total angular momentum. So sigma x square is equal to sigma square is equal to sigma x square plus sigma y square plus sigma z square equals to 3. So we already know that sigma x square is 1, that is a unit matrix, so our identity matrix. So that is in simplest form we used to write 1 and sigma y square also 1, here also 1. So 1 plus 1 plus 1 3 and s square is nothing but sx square plus sy square plus sz square. So Sx is nothing but half h cut sigma x. So h cut square by 4 sigma x square, h cut square by 4 sigma y square, h cut square by 4 sigma z square. So we are having in this manner. So s square is nothing but 1 2 3, 1 plus 1 plus 1 3. So 3 h cut square by 4. So s square is nothing but 3 by 4 h cut square. And next thing is, let's look at the properties of Pauli spin matrices. These properties already we have, by using these properties only we have made the derivation of these matrices. So let's have a look at this. So sigma x square equals sigma y square equals sigma z square equals to 1. So already we have done this based on the eigenvalues of sigma x, sigma y. So let's do a cross checking for this. So sigma x square, sigma x is nothing but sigma x square is nothing but sigma x into sigma x. Sigma x is 0 1 1 0 0 1 1 0. So on doing multiplication, 0 into 0 0, sorry 0 into 0 0 plus 1 into 1 1, so 1, 0 into 1 0 plus 1 into 0 0, so 0, and 1 into 0 0, 0 into 1 0, so 0, 1 into 1 1 plus 0 into 0 0, so 1. So this is identity matrix. Finally we are getting identity matrix. In a similar fashion we can do we can verify with sigma y square and sigma z square. So they also would be equal to 1. That is Pauli matrices are squared to identity. And next is eigenvalues of sigma x, sigma y and sigma z are equal to plus 1 or minus 1. This is the starting only we have discussed this one. And so eigenvalues. Pauli matrices anticommute with each other. So we have already derived this also. We have already found this anticommutator relation also from here in the process of deriving, equals to 0. So the same thing. So this is nothing but anticommutation of sigma x, sigma y equals to 0. That is sigma x into sigma y plus sigma y into sigma x equals to 0. In similar manner we would be having sigma y, sigma z, sigma x anticommutation equals to 0. So let's verify this. So sigma x is nothing but 0 1 1 0 and sigma y 0 minus I 0. So let's do matrix multiplication. 0 into 0 0 plus 1 into minus 1 1 into I plus I. So I 0 into minus I 0, 1 into 0 0. So here 0. So 1 into 0, 0, 0 into I, 0. 1 into minus I, 0 into 0, 0. Plus 0. So minus I plus 0. So here also the same thing. 0 into 0 plus minus I into 1, minus I. 0 into 1, 0, minus I into 0, 0. So 0 plus 0, 0. I into 0, 0. 0 into 1, plus 0. So here also 0. So I into 1 plus 0 into 0. So here we would get I. So finally, if we did calculation, we would get this. And if we add up I minus I, 0, minus I plus I, 0. So we are getting null matrix. And next thing is Pauli matrices are traceless. That is, trace of sigma I equals to 0 as Pauli matrices obey Clifford algebra. So if you see here, trace is nothing but sum of principal diagonal elements. So here 0 plus 0, 0. Here 0 plus 0, 0. Here also 1 minus 1, 0. So sum of the principal diagonal elements is 0. So trace of Pauli spin matrices is equal to 0. So these are nothing but the properties of Pauli spin matrices. Now let's have a look at their commutator relations. That is commutation of sigma x, sigma y. That is nothing but sigma x, sigma y minus sigma y, sigma x. That is AB minus BA. So sigma x is this 0, 1, 1, 0. Sigma y 0 minus I 0. So on multiplication 0 into 0, 0 plus 1 into I. And 0 into minus I 0, 1 into 0, 0. So 0. 1 into 0, 0, 0 into I 0. So 1 into minus I minus I plus 0 into 0, 0. So in the same way here also if we multiply we would get this. So here we are having minus sign here. So this is commutation. So minus into minus plus. So I plus I, 2I. And minus I, here also minus I, minus 2I. So 2 into I 0, 0 minus I. So this here if we take I as common. If I is taken as common. So here I into 1, here I into minus 1. So 1, 0, 0 minus 1. So this is nothing but sigma z. So 2I sigma z. So this commutation is nothing but 2I sigma z. So in the similar manner, we can prove that sigma y sigma. So in the similar manner, we can prove that sigma y sigma z, commutation equals to 2I sigma x, and sigma z sigma x commutation is equals to 2I sigma z sigma y. And next thing is another sigma x is sigma square equals sigma square equals to sigma x square plus sigma y square plus sigma z square. So if we do commutation of sigma square with sigma, so this is the commutation. So in the place of sigma square we are having this one and sigma x. Now we already know that commutation of a plus b plus c d is nothing but we have to distribute this plus sign. So a commutation of ad plus commutation of bd plus commutation of cd. So here also the same thing. Commutation of sigma x square sigma x plus commutation of sigma y square sigma x plus commutation of sigma z square sigma x. Now this commutation sigma x square comma sigma x is nothing but sigma x cube minus sigma x cube. So a cube minus a cube is nothing but 0. So this term would be vanished and these two terms would be remaining. So these are the remaining terms. So this sigma y square can be written in this manner, sigma y into sigma y. Here sigma z square can be written in this manner, sigma z into sigma z. So and we know that commutation of AB comma C is nothing but here A is on the left hand side. So we have to take it aside from the left hand side only. So A commutation of BC plus here B is on the right hand side. We have to take this B aside. So A comma C B. So based on this formula, now we have to apply this formula to this. So we have applied here. So sigma x, sigma y, sigma x. This is sigma x. And again sigma y has to be taken aside on the right hand side. Sigma y, sigma x, sigma y. Here also same. Sigma z, this sigma z taken aside, sigma z, sigma x. And this sigma z taken aside, sigma z, sigma x. So in this, and we know that commutation of sigma y, sigma x is nothing but minus 2I sigma z. So here we are already derived sigma commutation of sigma x sigma y is 2i sigma z. Here then commutation of sigma y sigma x would be minus 2i sigma z. So here we are having minus 2i sigma z. Here also again the same minus 2i sigma z. And zx, xy, yz, zx. If we go in cyclic order, we would get plus. So zx. So 2i sigma y. So here having already zx. So y is missing. So y. So it is going in cyclic order. xy, yz, zx. So we are having plus. But here it is not xy, but it is yx. So minus. And here x and y are present, but z is not there. So this is x. Here also same again 2i sigma y. So finally if we do multiplication, so we will get in this manner. So sigma y sigma z. So sigma y is on the left, sigma z on right. Here sigma z left, sigma y right. In the same way here also if we do, finally all of them would get cancelled. This term, this with this, and this with this. Finally 0 would be remaining. So commutation of sigma square sigma y or sigma square comma sigma z would be equal to 0 in the similar manner. Thus sigma square commutes with each component, that is sigma x, sigma y, sigma z. So this is nothing but Pauli spin matrices and their properties and their simple commutation relations. So thank you.